We're now going to look at some results of the nonlinear programming optimizations that we talked about in the last section of notes. We ran some simulations where we designed some optimized controllers using the fmincon to look at some different fast charging strategies, and we used the degradation models that we've talked about earlier in this chapter of SEI formation and growth and the lithium plating on overcharge. The first set of scenarios that we looked at, we initially had a cell that was resting at some state of charge between 10% and 90%. So we looked at 10%, 30, 50, 70, and 90%. Those are the values we've plotted here. And the charger was given exactly 2 hours to attempt to optimally charge this cell to 90%. So you can imagine if the cell was already at 90%, then it doesn't have to do anything. But it's interesting to see what it chooses to do. And if the cell is at 10%, obviously it has to do something to charge this cell up to 90%. And if it's somewhere in the middle, again, we'd have a different strategy possibly. In the constraints, we did not permit SOC to exceed 90% or to go below 10%, but we actually put no constraints on current. So the lower bound, we would say, was minus infinity, and the upper bound is equal to infinity. And fmincon has ways of incorporating that in its procedures to basically just remove those constraints. So current could be anything in the simulations that we did. SOC was between 10 and 90%, and we wanted to start with some initial SOC and after exactly 2 hours attain 90% SOC. And in the process, we wanted to minimize the capacity, the lithium that was lost due to side reactions. In the first set of results, we look only at the SEI growth degradation model. In the left-hand side, we see a plot of current versus time, and it's normalized to C rate. So 2C means a 2C current rate, and minus 2C is negative 2C, and so forth. The different colored lines are for different initial conditions. So the yellowish line is when we started at 90% SOC to begin with, and then all the way down to the blue line at the bottom, which is when we started at 10% SOC to begin with. Plotting current versus time is interesting. It's saying, and I see my sign convention here is different from what we often do, but this here is discharge, and this is charge current. It's maybe a little bit easier to see what's happening if we look at the plot on the right here that looks at state of charge of this cell versus time instead. And I got to tell you, the first time I ran this code and saw these results, I was surprised, but then I thought about it for a little bit and began to understand what was happening. Let's take the blue line first. We start at 10% state of charge. The optimum strategy, if I want to minimize the SEI layer that grows, or the capacity that's lost when I do that, the optimum strategy is to stay at 10% state of charge as long as I can, and then in the last little bit, about the last half hour, I charge the cell up quite smoothly to a 90% state of charge set point. Very interesting. Very interesting. You can see that in the current, so there's this kind of a ramping up of current that corresponds to that curvature there, and an almost constant current that gives me an almost constant slope right there. Very interesting to see that. And you go back to the plots that we made, the 3D plots of SEI growth, and we saw that for different states of charge and C rate, we would get different amounts of lithium loss. And if C rate was 0, the minimum lithium loss happened at the lowest state of charge. So that's why it's hanging out here. It's dwelling at this low state of charge as long as possible, because that's where I'm losing the least amount of lithium. And then I'm charging up to the maximum state of charge right at the very end, because even at resting rates, staying at that maximum state of charge has a high rate of lithium loss. That's why if we look at the 90% case next, this was the result that was perhaps surprising. The easiest thing to do is just leave the cell alone. Have zero current. It's already at the desired final state of charge. But that's not what the optimum strategy does using this model. The optimum strategy says I'm going to discharge this cell quite rapidly down to the minimum allowed state of charge of 10%. So SOC quite quickly goes down to 10%. Then it stays at 10% as long as it can, and then it follows exactly the same path from 10% up to 90% at the end. Again, if you go back and look at that figure, the 3D plot of what the degradation looks like, it makes sense from that perspective that if I just rest at 90% state of charge, I am degrading much more quickly than if I rest at 10% state of charge. And it turns out, using that model, that it's better to discharge than wait and then charge at the end. Very, very interesting result. How valid is the result? Well, we don't know. We'd have to try it out on real cells and have some way of electrochemically tearing the cell apart and measuring all of these quantities at the end to see if the model of degradation actually holds up under these conditions. Is the model of degradation right? If the model of degradation is right, then this is the right thing to do. If the model of degradation is wrong, then I have to start over and make a new model of degradation and try again. But it's still a very interesting result. And you have to ask yourself, even if this is the right result, is this what I want to do? Because in a real life situation, we might not know that I have exactly 2 hours to charge a battery cell. So when I plug in at night, maybe most nights I have 8 hours or 10 hours or some length of time to charge before I'm going to use the vehicle again. But what happens if I have a middle of the night emergency? I plugged my car in and it was maybe 70% when I plugged it in. And if all goes to plan, I'm going to discharge from 70% down to 10%, and then just before I need the vehicle, I'm going to charge it up to 90%, so I'm in perfect shape when I need the vehicle then. But if I have a middle of the night emergency and I need to use the vehicle right then, I can't. I don't have, I'm already at my minimum state of charge that I'm allowed to have. So probably, even if this is the right thing to do from a degradation perspective, it's not the thing we actually would do, but at least this optimization gives us perspective and allows us to make some intelligent compromises. Maybe we define for operational speaking that 10% is the minimum SOC, but for charging perspective that maybe 30% or 40% is the minimum. So we would discharge down to that level and then go across and charge up. That is a possible solution, and you'd have to do far more analysis on this to see, is it a really big difference in lithium loss between parking at 40% SOC, dwelling at 40% SOC versus 10%? Or is it really big? Then I really need to think about it carefully, or if it's not really big, then maybe I just wait at 40%. So this method at least gives us the chance of evaluating different alternatives and balancing what the math says is optimal versus what some human factors say is optimal. And what that really means is if the two are different, then the cost function was wrong. And I have to go back and think about how do I change the cost function to include more of the human factors in what it's doing, so that we can then get a real optimal answer from the math that's actually feasible as well. So this set of examples used the total amount of SEI, or lithium loss due to SEI growth, over the profile. We can also use the overcharge cost function or some combination. So here we redid the simulation using the lithium loss due to SEI growth plus the lithium loss due to overcharge together in the cost function, and we get an answer, a result that is qualitatively similar, but it is in fact not exactly the same. So again, this is a discharge here, and this is a charge there. The sign convention is opposite to what we are normally using. I might change that by the time you get these notes. And again, so notice we're discharging down to the minimum. We're dwelling at the minimum. We don't dwell as long, though. We actually take almost an hour to charge instead of half an hour. So adding the lithium loss due to lithium plating into the cost function has changed the optimum strategy. If I didn't consider lithium loss due to plating in my strategy, I was actually plating quite a lot in this because I was charging quite quickly, especially towards the end. I'm losing lithium especially towards the end because I'm charging quite quickly. So it turns out that the best thing to do, if I consider both of these models of degradation, is to charge more slowly and more smoothly, as we see here. There's a few bumps in this plot here. You notice there's kind of a stepwise decrease. That has to do with the way that I implemented the cost function. That's not real. So the real strategy is going to be a smooth line there, but you can kind of use your eye to put in what that would be. Looking at the optimum strategy, just for fun, I took the capacity loss of SEI growth plus lithium plating, and I added them together and I put them on this 3D plot, and I'm going to see if I can expand this a little bit for looking at it now. And on top of this plot, I overlaid the charging strategy from 10% to 90% SOC. So we start out there at 10% SOC resting, and we want to end up at 90% SOC, so that's this value. And if you look at the current versus time, you'll notice that we're not actually resting when we get there. We're still charging right up to the last point in time. So this here is that last point. And if this is kind of a parametric plot, we don't see time on this, but we're actually dwelling at 10% for a rather long time, and eventually around time, say 70 minutes, we start charging, and that initial charge is right here. And if I go back to current versus time, that's this right there. I go from 0C up to close to a 2C rate, and what that is doing is it is bringing me right to the edge of this cliff. Notice that there's kind of a Grand Canyon here where there's a sharp difference between no lithium plating and lithium plating basically, and SEI growth being factored in kind of smooths that edge off. But there is a place, there's a plateau of low degradation, and then there's above that, or on the other side of that plateau, there's high degradation. And the optimized controls basically goes almost as quickly as it can from the 10% state of charge to the edge of that cliff, and then it follows the edge of that cliff up until it gets to the point of 90% SOC, which is the desired final state. Now, the cost function well, the optimization procedure didn't really know that was the right thing to do. We just gave it a cost function, and it figured out that was the right thing to do, the optimum thing to do. And when we look at the result, we can intuitively explain why it's the right thing to do using these low degradation and high degradation regions. So I think that's an extremely interesting result, that it was able to find that on its own, and it makes a lot of sense, I think. This cost function here, you'll notice, kind of looks granular. So I pre-computed the cost function and stored it in a table is what I did. And that's why this is a jagged edge here, is because it's interpolating between table entries rather than exactly computing the cost at every point in time. It made the optimization a lot faster. So that's why I say the jagged edge there is more a factor, an artifact of the way I chose to do the optimization to make it efficient or fast, rather than the real result. If you look at that plot, you can understand that the real result is going to be smooth. So in this area here, we would expect smooth current changes versus time. So those are scenarios where we gave exactly 2 hours to charge, which is not exactly a fast charge. Then we did some more simulation scenarios where we looked at giving less time to charge. So still 120 minutes, 2 hours, but then also 115, 90, 75, 60, and so forth. This should be 105. I did it in 15-minute increments in order to charge from the initial state of charge to the final state of charge. And the results are shown here, and I don't show current versus time, I show only state of charge versus time. This is for using the SEI cost function only, and this is for using the combined cost function that uses both SEI and the overcharge lithium plating cost function. So for a 2-hour limit, starting, oh, by the way, these started at 50%, all of them. So starting at 50% for 2 hours, the best thing to do is to discharge to the minimum, rest, and then charge up, just like we saw before. For both of them, there's no change in the result here. We reran the simulation, but the result is the same. However, if I have less time, if I don't have 2 hours, I have only 1 hour and 45 minutes, we don't dwell quite as long at the minimum, and we still do get to the final. If I have 1.5 hours, I discharge to the minimum and then get up to the maximum. But then at some point there's a crossover where the strategy just optimally, automatically changes. If I have only 75 minutes, notice that I discharge a little bit, but not all the way, and then I charge up, so I do get to the desired final state of charge at the end. So that's very interesting. We don't have enough time in this case to get all the way down to the bottom and all the way up to the top, and so the best thing to do is this purple line instead of what we might have expected based on these lines right there. So I can almost follow that slope down and say, well, I maybe thought the best thing to do would be this. It looks like I have enough time to do that, but that's not the best thing if I did try to do that. Very, very interesting. And if I have less time than that, even if I have 1 hour or 45 or 30 or 15 minutes, you can see that there's different things that we would do in order to charge from 50% up to 90% in those amounts of time. If we include lithium plating, qualitatively similar things happen, but quantitatively different. Notice that here the 90-minute plot went all the way down to the bottom and then all the way up to the top, but here, because we charge more slowly when lithium plating is considered, I don't have time to get all the way down to the bottom and the top and do that optimally. And so the crossover is at a different point. And if I have only 15 minutes to charge, I have a very different result. It basically is saying I can't do this without lithium plating in 15 minutes. It's just not possible. And so I'm following some strategy for a while, and then at the very end I just jump. I have a very high pulsive current, a very, very high pulsive current right at the very end to get up to 90% SOC. And yes, I'm going to lithium plate when I do that. But if I have to charge in 15 minutes, that's the lowest cost thing to do. So very, very interesting results. And it just shows you kind of the power of this nonlinear optimization, the nonlinear programming, and it gives you a lot of insight into what the cost function is telling you, what the degradation function is telling you. And so we can make other degradation cost functions for different mechanisms in a cell, and we can apply nonlinear programming. And ultimately, if we model the most significant mechanisms accurately, we should be able to come up with optimum charging strategies in a way that looks like this. Well, we're almost done. There's one more section left where I'd like to talk about computing power limits in a dynamic scenario and some preliminary ideas we have on that before finishing this course.